The previous video, you have studied a bridge rectifier with four diodes. And here is the load connection. And here we'll take the output. The output of the bridge rectifier is this pulsating DC. The input is AC waveform and the output is pulsating DC. And the meaning of pulsating DC is it is DC. DC means direct current. It should flow in only one direction. Yes, it is in positive direction. We can call it as DC, but it has got some DC pulses. It means it is having both DC as well as a AC component. So that type of waveform is called as a pulsating DC output waveform. So this we got in the previous video, and that is bridge rectifier output. Today, I am going to discuss how to remove these pulses and how to make this DC as a pure DC or a constant DC. So for this, we should use one extra component to remove the pulses, and that is called as smoothing capacitor. It is a filter circuit. So we should filter the AC component and we should pass only DC and get the output DC output across the load. So the capacitor is called as a filter circuit, or sometimes it is called as a smoothing capacitor. You should connect across the output of the bridge rectifier. Then you take the output across the load. You will get a pure DC. Some amount of AC is removed from the filter circuit. So this is the dotted waveform is the waveform without capacitor. So without capacitor, if I eliminate this capacitor, I will get this dotted waveform. It is nothing but pulsating DC. If I connect capacitor and take the output, so this is the output I am getting. So dark black output. So this is the output I am getting across the load. So it is also having some ripple, but not so as the earlier one, the waveform without capacitor. So here the capacitor plays a very important role by charging and discharging its action. It removes the pulses. So when the pulsating DC output, when I get the pulsating DC at the output of the bridge rectifier, when I connect the capacitor starts charges to the peak of the pulsating DC. So after charging, the output is falling here. The capacitor starts discharges. So when before discharging completely to zero, the next pulse arrives. So the before completely discharging, the next pulse arrives, the capacitor again starts charges, again discharge, charge, discharge, charge, discharge. Due to these actions, so this much amount of pulse is removed using the capacitor. So this is waveform with capacitor. Now, this smoothing capacitor converts full wave rippled output of the rectifier into more smooth DC output voltage. Now we can see the effect on it has the rectified output waveform with the different values of smoothing capacitors. If I use different values of capacitor, how the ripple is removed and how the output looks like. So initially I use 5 micro farad smoothing capacitor. So it contains more AC component here. See, it is giving 3.6. The capacitor is discharging down to 3.6 volts in this example. So it charged up to the peak value and it is discharging to 3.3 volts. Now what I'll do, I'll double this capacitor. 10 times I'll multiply and then I'll keep the capacitor in a circuit. So 5 into 10 is 50 microfarad. If I connect 50 microfarad, then the capacitor discharges to 7.9 volts. So see the earlier one with 5 microfarad of capacitor discharged to 3.6 volts. From the baseline, I'm getting 3.6 volts. Here with 50 microfarad capacitor from the baseline, I'm getting almost 8 volts. So as you increase the value of the capacitor, so I'll get I'll get more pure DC across the output of the load. So a larger capacitance, in practical experiment, we connect large value of capacitor, approximately 1000 microfarad capacitor I'll connect. So which will store more charge. Less value of capacitor, it will store less charge. More value of capacitor, it will store more charge. And less value of capacitor discharge quickly charges and quickly discharges. More value of capacitor charges and discharges slowly. It discharges slowly. So when it discharges slowly, it will lead to better ripple reduction. So if the capacitance is too small, the capacitor will discharge quickly, and again the ripple will remain, and they will remain noticeable. So what type of capacitor we should use? We should use always electrolytic capacitor. So electrolytic capacitor will have the polarity positive and negative. It will have two leads, longer and a shorter lead. Longer lead is positive and shorter lead is negative. So you choose that capacitor depending on the load current and desired ripple. And what should be the voltage rating of the capacitor? This is very, very important to handle the peak voltage. So if you are using 12 volts rectifier circuits, if you are getting 12 volts across the bridge rectifier output, then you must use the voltage rating of the capacitor at least 50% higher than the peak voltage. So what is the peak voltage? 12 volts. 12 plus 15, 50% of 12 is 6. 12 plus 6 is 18. So you should use higher than 18 volts. So the standard value of capacitor is 25 volts. You should use 25 volts capacitor. If you use less voltage capacitor, the capacitor will burst. So for this purpose, the voltage rate is very, very important in the filter circuit. So, okay, so this is all about the circuit explanation of bridge rectifier with filter circuit. Now I'll show you how to construct this bridge rectifier with filter circuit in Proteus, and we'll give the different values of capacitor, and we'll observe the waveform, how it eliminates the ripple. So let us click on the Proteus. This is Proteus. I'll minimize it. Okay. Oh, so I should get this. Next, click on new project. Now I'll give the name of the project as full wave bridge rectifier with capacitor filter. With capacitor filter. Okay. Click next, 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 and finish. I'll get now I can draw the circuit. I can connect the components. Go to the component mode. Click here. Click on P. Search option. Here I'll search what you need. I need a AC voltage source. Just type V sine. So click on this. Click OK. So place here. I'll place here. This is V sine. Right click on that component, and in property you give 230 volts, 50 hertz AC supply, 50 hertz. Click OK. Next, what you need? I need diode 1N4007 diode. So it's silicon rectifier. Second one you choose. Click OK. You can connect in diagonal form, or you can connect in very easy manner. I'll show you. First diode you place on the right side here. Okay. Second diode exactly this side, bottom side. Third diode in the same line below this you place. and in fourth diode above this, and in this same line. Okay, now you connect all the diodes. This I'll move here. All you should make in one line so it looks nice. Okay, now you connect cathode and cathode. Okay, anode and anode. And cathode and anode. And this. Okay, now this should go to cathode anode terminal, and this to cathode anode terminal. Okay, so here you connect one capacitor. Take electrolytic capacitor. Electrolytic capacitor. This one, electrolytic capacitor. I'm taking this capacitor electrolytic, plus and minus, click OK, and place here. Okay, so right click on this, rotate clockwise. Now you bring little down and connect the output of the rectifier to positive, and from here to the negative terminal of the capacitor. And here we need one ground. Click on terminal mode, click on ground, click here and do the connection. Okay, now you connect one resistor across the capacitor. So search for resistor. Click on component mode, search for resistor. Generic resistor you take. You take this resistor only, 10-watt resistor. Click OK and connect here. And right click on this, move little up and connect this to resistor one end and connect this to resistor other end, and right click on this, select the property, click 1K, OK, then click on the capacitor. Now I'll show you with 5 microampere microfarad capacitor. So the connection is over. Now I need a CRO. Connect CRO here. Okay, so input I'll connect to one channel. Yellow waveform is input. Then across load, I'll connect the second output. That is blue one. Okay, now I should get this type of waveform. Now connection, everything is over. Now you run. Simulate the circuit. So I'm getting the CR output waveform here. So I'm not using channel C and channel D, turn it off. Channel C and channel D, turn it off. And the blue waveform, this is the output waveform because output I have connected to blue second channel, that is blue waveform. Now with 5 microfarad of capacitor, I'm getting more ripple. It has got both AC and a DC. So first what you should do, you should keep this in a ground. Now next you release to DC, you will notice the pulsating DC. Now I'll change the value of the capacitor. I'll stop the simulation. Right click on this, edit properties. I'll change to 50 microfarad. Okay. Then click on simulation. See, the output waveform, it is getting more smoother. Earlier, I was getting more ripples. Now I am getting more smoother DC. Now I'll change another value. I'll stop simulating this. Go to this capacitor, edit property. I'll keep the capacitor value as 1000 microfarad. 1000 microfarad. Click OK. Then start simulation. See, the capacitor DC voltage is almost constant. You can see the waveform here. So it is almost constant. Small ripple is present. That also I can remove. Stop simulating. Choose the capacitor value 2200 microfarad. Maximum you can connect 2200 microfarad. Again, click on simulation. Now you can see the DC is a constant DC here. Almost all ripple is eliminated. So in this way, with the help of the capacitor, you can remove the AC component. So you can remove AC and you can get the pure DC. This is your input waveform. Yellow line is your input waveform and output is blue. Almost it is DC. So both before that, I'll keep the channel A in ground and channel B also in a ground. I'll overlap both the waveforms. Now, a channel A is input, I'll keep it in AC, and channel B is output, I'll keep it in DC. Now you can see the constant DC. In this way, the capacitor plays a very important role to remove the AC component.